In this lab, we explore the concept of acceleration and tension in a system using an Atwood's machine. An Atwood's machine consists of two masses connected by a string that passes over a pulley. It is a simple device that helps us study Newton's second law of motion and how unbalanced forces causes objects to accelerate. By comparing the motion of the two hanging masses, we can calculate both the theoretical and experimental acceleration and see how closely they agree. This experiment demonstrates how the relationship between mass and force affect acceleration. When one mass is heavier, the system accelerates in its direction. The pulley changes the direction of the force so that when one side moves downward, the other side moves upward. By adding more pulleys, we can see how the system becomes more complex, changing how the acceleration is shared between the masses. A real-life example of how this lab applies is an elevator system. Elevators use pulleys and counterweights to balance the load, reducing the amount of force the motor needs to lift the elevator, just like an Atwood's machine. When the counterweight is heavier, the elevator moves up or down depending on the mass difference. Understanding this principle helps engineers design a safer, more efficient system that helps use less energy. In this lab, we analyze both a single and double pulley setup to understand how mass, force, and motion interact. The experiment helps us connect theoretical physics equations to real-world motion and identify sources of experimental errors such as friction, pulley weight, and misalignment.
Hello, my name is Conrad and I'll be doing the materials for our section. In this lab we use the Atwood machine, which is the pulley system right here. The main setup used to study acceleration and tension. It lets two masses move in opposite directions while connected by a string over a pulley. Second off, we have the string, which is this. It connects the two masses and transfers tension through the pulley. It must not stretch, or else the data would be inaccurate. We have the two mass hangers, which we have this one and this one on the bottom. One of them is 5 grams, which is this one, and then the bottom one is 10 grams. We hold the masses on each side of the pulley. Their weight is included when calculating the total mass as well. So, and then we have the sorted masses, where we have this one is 50 and the bottom is 120. And the purpose of this is to, we can change the mass 1 and mass 2 to study how mass differences affect acceleration. We have the stand, which is just the stand right here, which is separate from the Atwood machine. And it holds the pulley at a fixed height so the masses can move freely without hitting anything. We have the motion sensor, which is right here. We've used the motion sensor over the last few laps as well. It measures the movement of the masses, records the position, velocity, and acceleration graphs. We have a computer right here with Capstone software installed, which connects to the motion sensor to graph position time and velocity time data automatically. And we have the balance, which is over here. And we've used the motion sensor, the computer, and the balance through the majority of these labs. However, it's the first time we'll be using the Atwood machine and the clamps stand. Everything else has been used in previous labs. Thank you.
Hi, my name is Gregorio Olivas.
And my name is Conrad Sue, and we'll be doing the procedure.
So we first set up the equipment, we place the pulley securely on the stand and pass the string over the pulley and attach two different masses, between 50 and 200 grams, where M1 was greater than M2. We made sure that both masses hung freely and did not touch the floor. Then we recorded the masses. We measured and recorded the values of the masses 1 and 2, and we used them to calculate the theoretical acceleration, which is found through mass 1 minus mass 2 divided by mass 1 plus mass 2 all times gravity. We collected the data, which we passed the string through the pulley and started recording the experiment. We caught it at the end so that the mass holders did not hit the pulley, the floor, or someone. From the data, we collected experimental acceleration and percent error and took screenshots of the graph with the points we used to calculate the acceleration. We corrected errors that may have come from the friction in the pulley, an unbalanced pulley, or a short distance in the experiment. The data collection was difficult as our motion sensor wasn't working, and every group of our lab faced the same difficulties. It took an hour to find out how the pulley system worked. Next, we set up the double pulley system, which we selected 2 new masses and the masses in between 50 and 200. We added an extra pulley weight to our mass 1 to minimize the error caused by friction. M1 is greater than M2 plus 50.
In the next section, we collected the data from the double pulley. We recorded the data and ran it several times to get a nice straight line on the graph. We collected the data to calculate our experimental acceleration, and we took a screenshot of our graph to be added to our lab reports data and data analysis section. Next, we found the near zero acceleration, and we found the combination of masses that gave the closest acceleration to 0. We also screenshot this graph, and we considered the percent error we were having with the motion sensor, and in the conclusion, we will discuss the questions that were in the lab objectives. Thank you.
Yellow diamonds in the light, and we're standing.
Hello, my name is Jorge Valdez. This is our data analysis for Lab 7. So for this lab, we were dealing with acceleration for pulleys. So our experiment setup for our first pulley was higher mass on mass 1 and then a lower one on mass 2. And this was our acceleration, our theoretical acceleration setup. And then we had for our first mass, which was this one right here, it was 135. And then our second mass was 55. So our theoretical acceleration came out to 4.13 meters per second squared. And then this was the equation, the calculations that I did. And then from there, we did our experimental thing. I don't know. Okay. Anyways, and we got right here for our acceleration. We got 3.98. You can barely even see. It don't matter. Anyways, and then for our percent error on this one, this is our calculation, and it came out 3.6% percent error. So that one was for our first one, and yeah, that was the first one.
Hello, my name is Santiago Arras. I'll go ahead and be explaining the second part of our data analysis. So for our step 2 of this lab report, we went ahead and we added a second pulley, a little lower than the original pulley that we have, and we upped the mass on the pulley for M1. So we went ahead with a mass of 165 grams. We kept M2 the same, just to keep it kind of similar at the same time. So following this equation right here, we went ahead and we got our theoretical after a while. Right here, as you can see, after we punched it in, 2.8, that's our theoretical acceleration for the 2 pulleys right here in step 2. And then following through, we went ahead and we did our experimental. And as you can see over here on this graph right here, we went ahead and we got a nice clean straight line shot up of the perfect pulley experimentation. And after getting our acceleration on our experimental of 2.4 roughly, we went ahead, we plugged that in, we double checked our work, and then we got a percentage error of 14.3% to cap off of our data analysis. That's all.
Yellow diamonds in the light, and we're standing.
Hello, this is Casey Kelly, and this is the conclusion for Lab 7. So in this lab, we studied how different masses and pulley setups affect acceleration using an Atwood's machine. For our data, we compared the theoretical acceleration calculated using Newton's laws with the experimental acceleration, which is measured from the motion sensor. The percent difference between the 2 values showed how close our experiment was to the expected result. A smaller percent error means our results were more accurate, while a larger percent error suggests that outside factors influenced the system. During the single pulley setup, our percent error was relatively small, showing that the basic Atwood's machine worked as expected. However, in the double pulley setup, the percent error was noticeably greater. This is likely because the second pulley added more friction and rotational inertia, and the string tension was not perfectly distributed. The added complexity of the system made it harder to get smooth, consistent motion. Overall, today's percent error was greater than in previous labs. One reason for that was it took about an hour to set up the lab, and during that time, the equipment was not working properly, which delayed data collection and may have affected the motion sensor reading. Besides friction, other possible sources of error included uneven pulley alignment or wobbling wheels, slightly stretching or slipping of the string, misreading or lag in the motion sensor, human error when releasing the masses or recording measurements, and air resistance and vibrations in the stand. These errors caused small variations in acceleration that increased our percent difference. Despite these challenges, the lab successfully demonstrated how unbalanced forces create acceleration and how multiple pulleys can change the way force is distributed. Understanding these effects helped explain real-life systems like elevators or cranes, where pulleys and counterweights are used to lift heavy objects efficiently. So in conclusion, the lab reinforced Newton's second law and relationship between force, mass, and acceleration. Although setup difficulties and equipment issues led to higher percent errors, the experiment clearly showed how theoretical physics applies to the mechanical systems in the real world.
Yellow diamonds in the light, and we're standing.
Hi, my name is Gregorio Olivas, and I will be going over the credits. Start with the introduction, Kaysen did the conclusion, Conrad did the materials and the procedure, Jorge and Santiago did the data analysis, and I did the procedure and all of the editing. Thank you.
Do